Section 4.5 deals with absolute maxima and absolute minima. So before we've looked at local maximums and minimums, or local extrema. So local extrema is something that happens locally. So it's kind of like you can cup your hands around it and the graph has some highs and some lows, or peaks and valleys. Absolute extrema is the highest point or the lowest point. So we can say that if f of c is greater than or equal to all the other y's for all the x in the domain of a function, then since f of c would be the biggest, it's called the absolute maximum of f. For example, here in this middle picture, we have an absolute maximum right here at f of 0 equals 4, because the x value is 0 and the y value is 4. Similarly, if f of c could be said to be smaller than all the other y's for all the x in the domain of your function, then f of c is called the absolute minimum of that function. For example, here you have an absolute minimum at the point f of 0 equals 0. So this was the absolute maximum at the point f of 0 equals 4, and then for that graph it has an absolute minimum at f of 0 equals 0. Now this graph right here does not have a max because these arrows are pointing up, which means that it's going towards infinity. So for this first graph we have no absolute maximum. For this second graph, we don't have an absolute minimum because our arrows are pointing towards negative infinity. So for the second graph, we have no absolute minimum. And for this last graph, because we have one arrow that's pointing off towards negative infinity, we say we have no absolute minimum. And because we have an arrow pointing off towards positive infinity, we have no absolute maximum. So the absolute max is the highest point when you're looking at the arrows, when you're including positive or negative infinity. So for here, we had a highest point because our arrows were both pointing down. The absolute minimum would be the lowest point, and this is our lowest point because those two arrows are pointing up. But you're not guaranteed to have an absolute maximum or minimum. So let's kind of look at what the extreme value theorem is and then kind of continue on in this section. So the extreme value theorem says the following. If f is a continuous function on a closed interval, so on a closed interval AB, which means it won't have arrows that point off towards positive and negative infinity, then that function is guaranteed to have both an absolute maximum and an absolute minimum. Again, this is because in a closed interval, since we're not going towards positive or negative infinity, you're guaranteed to have a highest point and a lowest point. So let's go ahead and take a look at example 1. Example 1 says, find the absolute minimum and the absolute maximum over the indicated interval using this graph. So the first thing I need to do is I want to find the absolute max and the absolute min from -3 to +3. So do I have a absolute max? I sure do. My absolute max is at this point, which is at the point f of -2 equals 8. So I have an absolute max at f of -2 equals 8. Do I have a smallest value? Yeah, I have a smallest value right here at f of 2 equals -24. So I have an absolute min at f of 2 equals -24. I had a smallest value at f of 2 equals -24 and a highest value at f of -2 equals 8. What if I change it and now say, okay, well, we're only looking at the interval from -3 to 0, so only this piece right here. If I'm looking at only that piece, do I have an absolute maximum? Again, I'm guaranteed to have an absolute max and min on a closed interval, and I do have an absolute max on this interval. It's the same dot there. So my absolute max is still at f of -2 equals 8. And then for this particular graph, now my absolute min is right at the endpoint, which is f of 0 equals negative 8. What about the interval from negative 3 to 1? From negative 3 to 1 just extends us a little bit more than we were looking before. Right to here. In this interval, do I have a max? Sure, my max is the same as it's been. That absolute max is still at f of negative 2 equals 8. And my absolute minimum value now is at f of 1 equals, looks like negative 19. What about the interval from negative 2 to 1? So now I'm looking at the interval from negative 2 to 1. Do I have an absolute maximum and an absolute minimum in that interval? Again, I sure do. My max is still at the same point. My absolute max is still at f of negative 2 equals 8. And my absolute min is still at the lowest point there, f of 1 equals negative 19. Let's look at two more of these. What if we change the interval from 0 to 3? Do I have an absolute max and an absolute min? Again, I'm guaranteed to have both. Well, my absolute maximum value is at f of 0 equals negative 8. That's my largest value there. And my minimum value is right here at f of 2 equals negative 24. Finally, what about the interval from 1 to 3? Well, do I have an absolute maximum value? I do. My absolute maximum value is happening here on the end. And it's f of 3 equals, it looks like negative 17. And my absolute minimum value is f of 2 equals negative 24. So your maximum value is just your largest value. Your minimum value is your smallest value. So note, absolute extrema can occur either at the endpoints, like here we had a max at an endpoint, or at what's known as a critical number of f. Well, why is it occurring at a critical number of f? Well, recall, what are critical numbers? Critical numbers, or f, are going to be places where f prime of x is equal to 0, or where f prime of x does not exist, where it's undefined, as long as that x value is part of the domain of x. So look here, we often had the answer that our max was at negative 2, 8, and that our min was at positive 2, negative 24. Well, at those points, we have horizontal tangent lines, which means the value of that first derivative is going to equal 0. Absolute extrema, if it exists, again, it's going to occur at the endpoints of the closed interval or at the critical numbers of f. So how do you find absolute extrema if we're not given a picture? Well, if we're not given a picture and we're asked to find absolute extrema, what we do is first make sure that f is continuous over the interval that it's closed on. Most of the time it always will be. Then you find the critical numbers of your function over AB. Recall, your critical numbers are places where f prime is equal to 0 or where f prime does not exist. Then you evaluate f at the endpoints, f of a and f of b, and at the critical numbers, f of whatever the critical numbers are. Then your max is going to correspond with the largest number, and your min is going to correspond with your lowest number. So let's go ahead and find the absolute maximums and minimums of each of the following functions. So the first thing, again, that we were told to do is make sure that our function is continuous over the interval. Well, the function that I'm given in this example is negative x squared plus 4x plus 6. Well, that is a quadratic, and quadratics have domains that are all real numbers, so it's continuous over the domain of 0 to 5. 2, find the critical numbers of f, which means I'm going to need to find the first derivative. So if I find the derivative, g prime of x is going to equal negative 2x plus 4. So then I need to figure out where is this equal to 0 and where is this undefined. Well, negative 2x plus 4 is a line, so is there anywhere where it's undefined? No, it's continuous over its entire domain. So the only time that I'm going to get an answer here is when I set it equal to 0. So solving for x, I end up with x is equal to 2. Now, is 2 in the domain of the given function? It is. Why? Because again, the domain of a quadratic is all real numbers. So that makes this a critical number. So, step 1, make sure that you're continuous over your interval. Step 2, find the critical numbers. Step 3 says now evaluate f at the endpoints and at the critical numbers, which means I need to find f of 0, f of 5, and f of 2. So let's grab a calculator and find all of those values. We're going to do negative 0 squared plus 4 times 0 plus 6, and we end up with 6. Then our next one, I'm going to change my zeros to 5, and I end up with 1. And finally, the last one, I'm going to change my 5s to 2, and I end up with 10. So now, step 4 says, just choose. Your absolute maximum is going to be at the largest value. Well, the largest value is 10, so I have an absolute maximum at f of 2 equals 10. And then your absolute minimum is going to be at your smallest value. Well, my smallest value is 1, and these should all say g, not f, because our function was in terms of g. So we have an absolute minimum at g of 5 equals 1. So our max is at g of 2 equals 10. And our minimum is at g of 5 equals 1. Let's find the absolute maxes and mins for the natural log of x on the interval from 1 to 2. Now, the natural log of x has a domain of 0 to infinity, which means it's going to be continuous on the interval from 1 to 2. So step 1 is done. Step 2, find the critical numbers, which means I need to take the first derivative. So h prime of x is equal to, well, the derivative of the natural log of x is the derivative of x, which is 1 over x. Then we need to figure out where is h prime of x equal to 0 and where is h prime of x undefined. So set it equal to 0. 1 over x is equal to 0. Solve for x. Again, we can put 0 over 1 and cross multiply. 1 times 1 is 1. X times 0 is equal to 0. 1 doesn't equal to 0, which means that there is no place where this first derivative is equal to 0. Then, where is it undefined? Well, this guy's a rational function, and since it's rational, I can just set that denominator x equal to 0 and solve for x. Well, I'm already solved for x, so then I need to figure out, is this guy a critical number? Well, is it part of the domain? No, 0 is not included. How do I know that? Because of the parentheses. So this is not in the domain of h, which means it's not a critical number. So I don't have any critical numbers for this particular function. So then I need to do step 3, which is to evaluate at the endpoints. So I need to figure out what is h of 1 and what is h of 2. So grabbing a calculator, if I take the natural log of 1, I get 0. And if I take the natural log of 2, I end up with 0.693. So this is the natural log of 1, which is equal to 0. And this is the natural log of 2, which was 0.693. So my absolute maximum occurs at the largest value. Well, in this case, my largest value is 0.693. So I have an absolute max at h of 2 equals 0.693. And I have an absolute minimum at h of 1 is equal to 0. So when you're looking to find absolute extrema on a closed interval, the first thing you do is you make sure that you are continuous over that interval. Then you find the critical numbers of your function, and then you evaluate the function at the endpoints and at the critical numbers. Your max is at the highest number, and your min is at the lowest number. Now, just like we saw in those first 3 graphs that we looked at, if you don't have a closed interval, you are not guaranteed absolute extrema. So absolute extrema is not guaranteed if you end up on an open interval. So for example, for this, we have no absolute extrema because we have an open interval. There is no highest point or lowest point. So we have no absolute extrema for this graph. Same thing here with our open points here. We have no absolute extrema. And here again, no absolute extrema. So you are not guaranteed to have an absolute maximum and an absolute minimum on an open interval, but it's possible to sometimes have absolute mins or absolute maxes if they are the actual lowest point or highest point. So you're not guaranteed to have it, but it still can occur. So how can you figure that out without having to graph it? How do we find out if we have absolute extrema without needing to graph it? We're going to use the second derivative test for local extrema and put that together so that we can figure out how to find absolute extrema on an open interval. So let's start with just figuring out what the second derivative test for local extrema is. In order to use the second derivative for local extrema, the first thing you do is you compute the first and the second derivative. And then you find the critical numbers of f for where the first derivative is equal to 0. Then you compute the value of the second derivative for each one of the critical numbers you found in step 2. Now, if f double prime of c is less than 0, well, remember that would mean that we are concave down. Well, if you're concave down, you're going to have a max. If f double prime of c is greater than 0, recall that means that we are concave up. Well, if you're concave up, you're going to have a min. If f double prime of c is equal to 0 or it does not exist, then your test is inconclusive. So the second derivative test tells us quickly if something is a max or a min. What we do is we find the first and second derivative. We find the critical numbers of f, which means that we're looking for the places where f prime of x is equal to 0. Then we plug those numbers into the second derivative. If the value of the second derivative is negative, then we have a max. If the value of the second derivative is positive, then we have a min. So how do we put that together with absolute extrema? Because that was talking about local extrema. Well, if you have an open interval and you want to find out do you have an absolute max or an absolute min, we say the following. Let f be continuous on an open interval with only one critical number in that interval. That's the main part. You can only have one critical number in that interval. If the first derivative is equal to 0 at that point, and the second derivative is greater than 0, so positive, again, remember that means concave up, then you're going to have an absolute min at that value. If the first derivative is 0 at that point and the second derivative is negative, recall that's going to be concave down, well then you're going to have a max at that point. So as long as you're only getting one critical number in the interval that you're looking at, you can use the second derivative test to determine if that is an absolute max or an absolute min. So let's do a couple examples of that. So it says find the absolute max or absolute min if it exists for each of the functions. We're not given an interval, which means that I'm looking at the interval from negative infinity to positive infinity. So I'm looking at all real numbers. So how do I do this? Well, I need to perform the second derivative test. So the first thing I do is find the first derivative. Well, the first derivative here is 6x minus 4. Then I find the second derivative. Well, my second derivative is 6. Then I need to find the critical numbers. So I just need to figure out where is this thing equal to 0. So 6x minus 4 equals 0. So 6x is equal to 4, and x is equal to 4 over 6, which reduces to 2/3. So then I need to figure out what is the value of the second derivative at that point. So what is f double prime of 2/3? So f double prime of 2/3, well, there's no x to plug in, so the second derivative is always 6. Well, 6 is a positive number, which means that we would be concave up. And if we're concave up, then we know that we have a absolute min. So therefore, we say that we have an absolute minimum at f of 2/3. Now to figure out what the y is, we need to plug 2/3 back into our original function. So let's go ahead and plug that in back into our original function here. So we have 3 times 2/3 squared minus 4 times 2/3 plus 9. Hit enter, and I'm just going to make this way into a fraction. So I hit math, and then I hit enter again, and enter, and I get 23/3. So my absolute minimum is that f of 2/3 equals 23/3. Now, I did not have an absolute max. How do I know I don't have an absolute max? Again, you can only have one critical number. We only had one critical number, and the value of the second derivative at that number was positive, which means I'm concave up, which means that this guy has got to be a absolute min.